Hello everyone, I'm back with a new video, same as a problem solving with the IR NMR spectra. So let's start this problem. First of all, always look for the molecular formula to get the Soder number. So here the molecular formula is given as C9H11NO2. So let's calculate the Soder number. You know that there is a nitrogen, so the equation will be a little different. If you don't know what equation I'm talking about, just watch my video on Soder. So here the equation will be x plus 1 minus y minus number of nitrogen by 2. So here x is like number of carbon, that is 9, plus um, 1 minus y is the number of hydrogen, that is 11, minus number of nitrogen is 1 by 2. So 10 minus 11 minus 1, 10 by 2, that means 5. So our Soder number is 5. So in my previous video I told if you have the Soder number 4 or more than 4, then you can consider you have the aromatic ring, like a benzene ring. So for a benzene ring, your Soder will be 4. So because it's a full ring, so 1 Soder, and there is a 3 alternative bond, so a double bond, so there are 3 more, so total 4. So 4 Soder will be gone here, but originally you have Soder 5, so still you have 1 more Soder. And remember, you have 2 oxygen in your molecule. So here if you see here 2 oxygen in your molecule, so for 2 oxygen you can think it could be carboxylic acid, it could be ester. So what are the conditions to be carboxylic acid? So you have to have a carbonyl peak that is around in IR, that is around 1700. Along with, there should be a ugly broad band from 2500 to 3000. So here let's see in the IR. In IR there is a peak that is 1680. So we can say it is not 1700 but 1680, but still we can take this is a carbonyl peak. I will explain why this is a carbonyl peak, like why it is below 1700. So that means you have a carbonyl peak, okay? And if your carbonyl peak somehow the electron density pulled out from the carbonyl peak, then your carbonyl carbonyl group, then your carbonyl peak will show up little less than the 1700. So now, since from the Soder we are thinking we have the benzene ring, and now you have the carbonyl peak, and if it is directly connected to the benzene ring, so like this, whatever the other part, so that carbonyl electron, that benzene ring is always like moving electron, that pi is circulating, okay? And during this pi circulating, that electron pull can be like pulled to the ring, and that's why sometimes your carbonyl group peak sometimes decreased that than the 1700. So I hope you understand. There are some other things also, like, so if you have a carbonyl peak along with like NH2, that is called amide. So this amide case also, the carbonyl peak always come lower than like 1700. That is like around 1690, 1680, something like this. So we're not going there. So now from the IR, what information we get, we have the carbonyl peak, and there is no band from 2500 to 3000. So there are no band here, like no band. So it is not carboxylic acid. So we can assume that since we have 2 oxygen, it could be ester, okay? And since we are confirming that we have a carbonyl group, so in that case there is 1 double bond. So for this 1 double bond, other Soder number will cover. So total 5 Soder. So since we determine we have total Soder 5, so 4 for the aromatic ring and 1 for the carbonyl group. So soda equal to 5. So benzene ring 4 and carbonyl group 1. Okay. And in your UV spectra, normally if you see the peak around like 270 or something, so you can think it is like N to pi star transition. So it is not very important here. So but from the IR definitely we get that information. Now go to the and you definitely you can calculate the molecular mass, how much you should get from here, like according to my previous video. So you should get 165. Now let's see, like first of the proton NMR, then we will come back to the carbon NMR. And since from the soda we are saying we have aromatic ring, what is the proof? If you see my previous videos, then you should understand we have aromatic ring. That means in the proton NMR the peak from 6.5 to 8.5. So that peaks definitely for the aromatic ring, like benzene ring. Any benzene ring always give you the peak around that area. Okay, so this is the proof that we have benzene ring. Like there are two signal here, and those are like two doublet. Okay, two doublet. So it is a doublet and it is a doublet. And from my previous video you should know, like this is a distinct spectra for what kind of aromatic ring. So yes, so I told last time, if you have 1,4 disubstituted benzene ring, like 1 and 4 position having something, so in that case it should give you two doublet. So there are two different kinds of proton, okay, like this. So if it is A and it is B, so similarly it is also A and it is B. So this A is saying B, so A will give you a doublet, but there are two A, so that's why it can be saying like 2H, because see here, like this is for one proton and this is for another proton, like this is for two proton total, two proton, and same integration value, this is for two proton, and that's why so this is for two proton and this is 1, 2 and 3, so this is total 3 proton. Okay, so 3 proton triplet, that means this is a methyl group definitely, and since it is triplet, that means it has a neighbor has a CH2. Okay, and that CH2, now that CH2 has a neighbor as a methyl, so that CH2 will give you a quartet. So it is giving you a triplet, that is triplet here, and that CH2 will give you a quartet. So let's look for the quartet. Yes, we have a quartet here that is around 4.2 to 4.3, something like this, along with a broad peak. So let's discuss the broad peak later. So first let's talk about this quartet. Okay, that quartet, but since this quartet is above 4, that means that quartet is giving you like CH2 peak, right? That CH2 is there, but since it is above 4, and so from my previous video you should know already, I told couple of times, if you have any proton having in the carbon that is next to the oxygen, so it will give you the peak like downfield or de-shielded peak. So that means you have oxygen next to this CH2. Okay, and since we are saying like we have a carbonyl group and it is S star, suspecting S star, so we can attach these things there. So we got one group here, and let's see in the carbon NMR. So this is proton decoupled and it is off resonance decoupled. So since this carbon is giving you a quartet, that means a carbon having 3 proton attached to it. So 3 plus 1, it will give you a quartet. That means it is a methyl carbon. And this carbon is giving you the triplet. That means this carbon has a 2 proton attached, in it. So this is a CH2 proton. And also the CH2 proton that is showing up near like 60. So any carbon along with oxygen always show up in this region, like 50 to 60 ppm. You can remember that part. And in the since we said in the aromatic ring, like we have benzene ring, okay, and in the benzene ring we are saying it is 1,4 disubstituted. So let's count the carbon, okay, types of carbon. So it will be 1 carbon, and then it will be another carbon. These two will be the same, and there will be another carbon. These two will be also the same, and this carbon will be the different. Okay, so now total types of carbon. So this is 1, this is 2, this will be 2, this is 3, and this is 4, and this is 3. So 1, 2, 3, 4. In aromatic region you should get 4 carbon. So here this is 1, this is 2, this is 3, this is 4. So we have 4 different carbon, and all those carbon in the proton decoupled, those will be doublet. So you are seeing 1 doublet, okay, and this is singlet because there are actually 2 singlet. You should see 2 singlet, 1 and 4. So definitely 1, and this is maybe 4. So 4, and this number is in the 1. So it could be 2 and it could be 3. Okay, so because they have proton in it, 1 proton, so 1 proton, it will give you the doublet. So let's don't think too complex way, just we should have 4 different carbon. You are saying 4 different carbon, and since we are saying like we have 1 carbonyl group here, so so we have 1 carbonyl here, and that carbonyl peak is here, like 165. So another thing, like 162 to 171, something like this, or 175 are ester carbonyl group. Okay, so now we have these things, but remember that now count the total number of carbon and how many carbon you already have. So we have in the benzene ring there are 6 carbon, and in this chain we have how many carbon? So 1, 2, and with the carbonyl 3. So this is 1, and this is 1, and this is 1. Okay, so here 3 and 6, 9. In the structure molecular formula we have 9 carbon, so you already get 9 carbon. Now the number of proton in the structure, it has proton is 11 proton. Okay, and how many proton we got it from here? Like in the aromatic ring there are like 4 proton total, and CH2 CH3 there are like 5, 4 and 5, 9 proton. So we have 11 proton, 11 minus 9, so still we have 2 proton remaining, like we don't know where it is. And in our molecule we have 2 oxygen, both oxygen we have found, so remaining is nitrogen. So you have 2 hydrogen and 1 nitrogen, so you can imagine you might have the amine, okay, NH2 group. And now how you will prove? First of all, it is a primary amine. You can go to the IR. In the IR in my IR video I explained, if you have the primary type amine, then you have 2 hydrogens, so you will get 2 band around 3300 to 3400. So you can see easily 3327 and 3410, there are 2 band. That means it is a proof that you have a amine group in your structure. Okay, and there is another thing. If you now you can see here that your one of your peak is showing exchange with deuterium oxide. So this broad peak exchange with deuterium oxide, this is also proof of couple of things. It could be OH, or it could be carboxylic acid, and it could be, finally it could be like amine. So if you have NH2, then those peaks normally exchange with the deuterium oxide. But since we already get all other correct information from the proton NMR and carbon NMR, like these chain like CH3, CH2O and ester group here. So here we can confirm that we have this group CH3, CH2O, C double bond O, and also benzene ring. So we can attach those things. Like now we also kind of confirm from the IR that we have amine group. So now you can just connect all those pieces together to get the structure. Let's see what is the structure looks like. So I hope you can draw it, but still I can show you how it would look like. So I can draw the aromatic ring horizontal way like this, and we have one NH2 group and one carbonyl group directly attached to the benzene ring. That's why that carbonyl is showing up in the IR like little less than the 1700, and then it should be O, and then it could be CH2, then it could be CH3, and it is perfectly matching with the proton NMR. Now you might say, what if we have the structure like this? So suppose NH2 is okay, but what if we can also think like that, right? Like we can put oxygen first, and then we can put CH2 and then CH3. So that also kind of close structure, right? But how can we confirm that the top one is correct one? Like why not the bottom one? So remember that. First of all, in the IR, the carbonyl group peak is giving less, and because it is attached to the aromatic ring. And here, the carbonyl group is away from the aromatic ring. So that is one problem. Another problem is in the proton NMR, you see the CH2 peak is above 4.2 or 4.3. That means that CH2 need to be next to the oxygen. So if you think the bottom structure, this second structure, then that CH2 is not next to the oxygen, okay? So that is not matching with this. So in that case, that CH2 quartet could come up around like this. Sorry. So that quartet could come here like this. If that structure is correct, then you should see the quartet here, not there. So that's how this is the signature peak here in this NMR. So in this molecule, like this is the signature peak actually. This CH2 peak next to the oxygen. That's why it can be changing. So this is the final structure. So if you have any question, just ask me in your comment section, and keep practicing more structures, and I will bring more more complex structures, so that you can slowly build up your expertise or knowledge on the spectroscopy. And please subscribe my channel if you didn't do it yet. And thank you for watching my video. Bye now.